start, let's talk about perfect square numbers. When we multiply a whole number by itself, we get a new number that's called a perfect square. For example, if we take 6 and multiply by 6, we get the perfect square number 36. Now the reason we call this a perfect square number is probably geometrical in nature. If we were to draw a square, and each side length of our square is 6 units, then the area of our square is going to be 36 units squared. Now along with the term perfect square comes another term that we call the root of the square. The original whole number that we multiplied by itself to get our perfect square is called the root of our square. In my opinion, it's really beneficial to know the perfect square is up to 12 times 12. If you already know your multiplication facts, then these ones are going to come naturally for you. Let's say we're given a perfect square number, and we want to determine the root of our perfect square. So, for example, maybe we're given the number 36, and we'd like to figure out what number multiplied by itself is equal to 36. Well, if we want to display this computation in mathematics, we use a radical sign, or our square root sign, to indicate this computation. Remember that 6 times 6 is equal to 36, so we would say that the square root of 36 is the number 6. A radical expression is any mathematical expression that contains a radical sign. Now for us, we're going to say that a radical expression is in simplest form if there are no perfect squares underneath our radical sign. So, for example, the square root of 13 and the square root of 65 are in simplest form because 13 is not a perfect square and 65 is not a perfect square, and neither of these numbers has a factor that's bigger than 1 and is a perfect square. On the other hand, the square root of 16 and the square root of 8 are not in simplest form. That's because we can rewrite the square root of 16 as the number 4, and 8 contains a factor that's bigger than 1 underneath the root sign that happens to be a perfect square. So 8 we can rewrite as 4 times 2. And 4 is a perfect square. It's 2 times 2. So we're going to see in a couple of slides how we deal with these radicals that are not in simplest form. Let's go ahead and do some calculations with square roots, starting with the square root of 64. Well, we know that 8 times 8 is equal to 64. This means that the square root of 64 must be equal to the number 8. And that's all there is to it. Next, let's move over here to the square root of negative 144. Now this one's a bit challenging because you might be tempted to say 12 or negative 12. But let's take a look at a couple of equations. The first one is that 12 times 12 is equal to 144. That I definitely agree with. I also know that negative 12 times negative 12 is going to be equal to 144 as well, because our two negatives are going to cancel out and make a positive. So this means that there are not two numbers that we can multiply together that give us a product of negative 144. In general, we say that any square root where we have a negative number underneath is not a real number. We're not going to be able to evaluate it using just real numbers. If you do take some more math courses, what eventually happens is you can evaluate these square roots using what are called complex numbers. Next, let's move on down here where we have 3 times the square root of 100. Well, we know that 10 times 10 is equal to 100. This means that 3 times the square root of 100 must be 3 times 10. And that gives us a final answer of 30. In our last question, we have the square root of 9 minus the square root of 4. 3 times 3 is equal to 9, so the square root of 9 must be 3. And 2 times 2 is equal to 4, So the square root of 4 must be equal to 2. This means we get a final answer of 1. Next, let's work through a couple of questions and try to figure out if our radical expressions are in simplest form. Let's begin with square root of 32. Now, recall that 32 can be factored into 4 times 8, or into 16 times 2. So this means that there is a factor that's bigger than 1 that is a perfect square number, either 4 or 16. So this means that the square root of 32 is not in simplest form. Next, let's look at the square root of 17. Well, the only way that we can write 17 is 17 times 1. There's no other way to write this number because it's prime. So this means there are no factors of 17 that are perfect squares. So this particular radical expression is in simplest form. For the number 22, besides 1 times 22, there's only one other way to write the number 22, and that's 2 times 11. Neither of these numbers are perfect squares, so we would say that square root of 22 is in simplest form. We can't simplify this one any further. For the number 50, we know that 50 is 2 times 25. And 25 is a squared number, that's 5 times 5. So this means that the square root of 50 is not in simplest form because it does have a factor that is a perfect square. Now something we saw earlier was that we have radical expressions that are not in simplest form. So you might wonder, how can we change that radical expression and get it into simplest form? Well, we do that using the following property of radical expressions. If a and b are positive real numbers, then the following thing is true. We have that a times b, underneath the square root sign, is equal to the square root of a times the square root of b. Now, if you want to see this with a numerical example, let's take the number 36. We know that the square root of 36 is equal to 6. But it's also true that 36 is equal to 9 times 4. So this property says we can take our square root sign and we can distribute it to both the 9 and the 4. The square root of 9 is 3, the square root of 4 is 2, and multiplying these together we get 6, which is exactly the same number that we got before. So this is a strategy that we're going to use to simplify our radical expressions. So let's go back to those two radical expressions that we couldn't simplify before, but we knew were not in simplest form. And we're going to use the product property to simplify these radical expressions. So remember that 32 we could write as 2 times 16. And using the product property, we can break apart this square root into square root of 2 times square root of 16. Square root of 2 is in simplest form, but the square root of 16 we can rewrite as 4. We know that 4 times 4 is equal to 16. Generally, we put the square roots second and the integer numbers first. So I'm just going to rearrange this. We'd usually write this as 4 root 2. For the number 50, we know that 50 is 2 times 25. And using the product property, we could rewrite this as square root of 2 times square root of 25. And the square root of 25 is 5. And then we just do quick rearranging to get 5 root 2. Now I know that I've mentioned this already in the lesson, but I figured I would say it one more time, and that is the idea of negative square roots. If we're going to use a square root radical sign, we have to make sure that our value under the square root is positive. Any negative number represents a number that's not a real number. It actually represents a complex number. So just be aware of this as you're working through your examples. All right, my little epsilons, stay positive.